Welcome to qnawire.
In this problem, we will let capital omega be the angular velocity of the cab, small omega to be the angular velocity of the blades relative to the cab, and hence the absolute angular velocity of the blades is capital omega plus little omega. The information we are given is that initially the blades are revolving at 180 RPM, which is revs per minute. And this is relative to the cab. 180 revs per minute is equivalent to 6 pi radians per second. So we're just converting them to usable units. Omega 2 in state 2 is 240 RPM. Remember, one revolution has 2 pi radians and 1 minute has 60 seconds. So the rotation of the blades increases to 240 revs per minute, which works out to 8 pi radians per second. Now we also know that the mass moment of inertia of the cab, IC, is given as 650 pound/foot/second squared. And the moment of inertia for the blades, IB, is equal to, since these are thin flat rods, 4 times 1 over 3 times the mass times L squared. And this is equal to 4 into 1/3. And the mass of the blades is its weight, 55 pounds, over 32.2 feet per square second. So the weight divided by G. And L is 14 feet all squared. And so we get the mass moment of inertia for the blades is 446.38 in the same unit as that for C, for the cab. That's pound/foot/second squared. And what we're told is that the cab does not rotate. So capital omega 1 is equal to capital omega 2 is equal to 0. So only the blades are rotating with respect to the cab. And so what we will do here is initially we will take moments about the shaft. So the momenta, from the principle of momentum and impulse, the momenta of the particles that comprise the blades initially plus the external impulse must be equal to the final momentum of the system in its second state. So if we take moments about the shaft, we can equate the moments from position 1 or from state 1 to state 2. So the moments initially is due to the moment of inertia of the blades into the rotation omega 1 plus capital omega 1 plus the contribution from the cab IC times capital omega 1. And then we have the impulse, in which the rotation of the blades increases. The impulse is FRT, where F is the weight of the cab. And this is equal to IB into the second state omega 2 plus capital omega 2 plus IC capital omega 2. So we know capital omega 1 and capital omega 2 are 0. So what we are left with is that FRT is equal to IB into omega 2 minus omega 1. And these values are all known. So FRT is simply 446.38 into 8 pi minus 6 pi. And so we get FRT to be 2,804.7 pound feet square second, or pound feet second. So from here we can see that the force times the time, Ft, is obviously FRT divided by R, which is 2804.7 over 16 feet, the length of the blades. And this is 175.29 pound seconds. So we'll see why we did that in a moment. So now that was the angular moments. Now let's look at the linear components of the momenta. So the linear components give us mv1, the linear momentum initially of the blades, plus impulse ft is equal to mv2, the linear momentum of the blades, when the speed is increased. So from here we can see that v2 minus v1 is equal to ft over m. And this is f times t, we calculated to be 175.29. And the mass of the blades, m, is, or the mass of the cab and the blades together is the sum of the two, which is 1250, the weight, over g, which is 32.2, plus 4 times the mass of the blades, which is 55 over 32.2. That's the entire mass of the cab and the 4 blades. And hence we get v2 minus v1 to be 3.8398 feet per second. But that's v2 minus v1. But remember, we want to find the horizontal velocity of the helicopter in the second state. So remember v1. So v1 is equal to 0. So initially the helicopter is at rest, the cab is at rest. So v1 is equal to 0 implies that v2, the velocity that we require, is simply what we calculated above, and that's 3.84 feet per second. Secondly, we wish to calculate the force. So the force F is equal to Ft, which we have a value for, divided by time t. So that's the impulse, obviously, divided by the time over which the impulse acts. So that's 175.29 over a time of 12 seconds. Hence we get the force to be 14.61 pounds.